Hello, everybody. Welcome to our last session of the Expo 2022. I hope you had a great 2 days and many interesting presentations to join. Maybe also join some of our presentations before. We are the KnowWhereGraph project, and in this last session, we are going to discuss how to build the future knowledge graph infrastructure for the United States. We have a couple of speakers or panelists, so to speak, here, Pascal Hitzler, Shirley Stevens, Mark Schildhauer, and Tommy Thelen, just in the order that I'm seeing them here on my screen. And we are going to basically essentially have a nice chat that you're welcome to listen into. And hopefully this will be interesting to you. And then please either raise your hand or unmute yourself or type something in the chat that we are also going to monitor. And then we can make this as interactive as you would like. I know these systems are a little bit odd and difficult to get used to, so be patient with us, and we are going to find a way to communicate with you. So maybe before we start diving into some of the interesting questions we want to discuss, I would suggest that each of you very briefly introduces yourself with just, a sentence or two, and we're just going to do this in the order of my Zoom screen. So Pascal, you would be first.
Pascal Hitzler, Computer Science, Kansas State University. And I'm mostly known for my work on semantic web, recently focused on ontology modeling. I'm also doing quite a bit on neurosymbolic integration recently, so general artificial intelligence.
Super, thank you, Pascal. Shirley, you would be next.
Hello, everyone. My name is Shirley Stephen. I'm a postdoctoral scholar at UCSB. I work a lot with ontologies, and I'm currently working in the KnowWhereGraph project, helping develop ontologies and triplifying data for ingestion in the knowledge graph.
Awesome. Thanks, Shirley. Mark Schildhauer is next.
Hi, I'm Mark Schildhauer. I'm from the National Center for Ecological Analysis and Synthesis, also called NCES at UC Santa Barbara. My background is in ecology, but I've been director of computing until recently, semi-retired, as my presence here is indicative of. And very interested working with the Data One project, and we're very excited as well about how the semantic approaches we're taking, especially on KnowWhereGraph, can help integrate lots of environmental data.
Fantastic. Thanks, Mark. Tommy, you are next and last.
Hi, I'm Thomas Thielen. I also work at NCES. I work as a full stack developer, working on various research projects, helping people realize the software that they dream of.
Well, fantastic. So maybe we just dive into our first questions here and have this an open discussion. So if I have a question that matches your interest, then just speak up, and that's true for the panelists here. But keep in mind, if you are joining us as part of the audience, then you can also jump in at any second or type your questions in the chat. So before we talk about knowledge graph, let's talk about the term that maybe is more familiar to a little bit less technical audience, and that's FAIR. And maybe at first you may be thinking, how is FAIR and FAIR principles related to knowledge graphs? But the F and the I and the R obviously are about finding and integrating data and making data more reproducible. So let's explore this relation for a second here together. How do you feel do knowledge graphs, folks, fit into this FAIR principles picture? I'm not sure who wants to take the question, and I leave it between you guys to start talking. Mark, go ahead.
Yeah, coming from NCES, which is a synthesis center, which all of the projects that we sponsor there necessarily bring together a lot of heterogeneous data. Synthesis is bringing together a lot of different data, and so the article, that coined FAIR by Mark Wilkinson and Michel Dumontier really, I think, galvanized the data repository world into, it gave them a very catchy acronym, right? Findable, accessible, interoperable, reusable. And then in that paper, they described, minimally what would be necessary to make all the data being collected by researchers more fair. And, sort of covertly, they were indicating essentially the type of semantic approaches that we've been pursuing with KnowWhereGraph. They did mention XML and RDF. They were very delicate about it, but my interactions with the data repository world, the environmental data repository world, especially such as at RDA, the Research Data Alliance, or the ESIP Federation, they're all very concerned about making their data more fair. And I think that KnowWhereGraph is really kind of paving the way for those repositories to better get a grip on how to best make that vision happen. So I think that FAIR was a wonderful viral acronym, and that KnowWhereGraph is right directly in the fast lane on making FAIR.
I love your answer, Pascal. Go next.
So just to add to this, and of course I completely agree with Mark here. It also makes sense to look a little bit kind of at the history, right? I mean, knowledge graphs themselves are really an outflow of the work done in the semantic web field for 20 plus years. I'll post a link to a historic overview which kind of explains it a bit if you're not so familiar with that. And at the same time, the FAIR principles, which was really kind of, as Mark said, it galvanized the field, right? It kind of boiled it down to some essentials, which were at the same time formulated generically enough, right, that it just makes sense. But again, kind of when they came out and reading that, if you were from within the semantic web field, you were more like, yes, exactly, right? So they just managed to express it better than many people before that. But that's what the field is about, right? So from that perspective, knowledge graphs and all the other semantic web technologies which kind of fuel them and FAIR are really tightly intertwined in terms of, well, they come out of the same things from 20 years ago and are still kind of going step in step together.
Yeah, the set of authors is also overlapping quite a bit, right? Shirley, Tommy, do you want to jump in, or should we continue with the next question?
I was just wondering, since Mark mentioned KnowWhereGraph, if anyone else, it's not like an answer, but more of like a question to the other KnowWhereGraph people in this panel. Since we're talking about FAIR, when we talk about KnowWhereGraph, what are the steps that we are taking to make KnowWhereGraph FAIR? Mark said KnowWhereGraph is one of is like primarily goal-oriented towards being fair, right? So concretely, what are some of the steps we do to make it fair? And one of the primary things that I think of when it comes to FAIR is trying to model metadata, rich metadata and provenance information for all the information that we have in KnowWhereGraph. If anyone else wants to add anything else.
Well, actually, I think, go ahead,
Yano. Well, I was just going to say that we can go right down the FAIR acronym one by one and articulate exactly why KnowWhereGraph and the W3C semantic web recommendations essentially enable FAIR. The findability is the dereferenceable HTTP URIs that lead into rich expressive semantics in ontologies. The accessibility is also, again, leveraging the web. So the web is really essential here. The interoperability is the languages like RDF, RDFS, OWL, Shackle, not your, your idiosyncratic ER schema. It's expressing the schema in a highly extensible way, in addition, using those W3C recommended languages. And the reusability would come from the opportunity then to share some of those vocabularies and ontologies, across the entire internet. So there you have, FAIR right there, completely embodied in our approach with KnowWhereGraph.
I absolutely agree, but I think it was important to establish this relation because I think that the FAIR term, as you just introduced before, Mark, is so widely visible because it's not only an important set of principles, essentially, as we just said, based on semantic technologies, but it's also nicely boiled down into something, that is all close to our hearts, right? And the FAIR part, of course, in the FAIR matters greatly. So actually, that's a nice start to another question that I wanted to get your feedback on, namely that obviously if you design such a knowledge graph for the future of the for the US public and industry, we need to agree on what goes into such a first knowledge graph and what shouldn't. Obviously it can grow and grow, but in your perspectives, are there certain types of data that are specifically suited or suitable for knowledge graph integration, and maybe other data sets that wouldn't fit so well? Mark, go ahead.
Coming from an environmental synthesis center and having worked with many dozens of working groups that are struggling to integrate their environmental data, I would say environmental data in particular are highly amenable to being ingested into a knowledge graph. But in addition, we're the KnowWhereGraph because environmental data always has an important spatiotemporal context. So it's extremely useful for incorporating into the graph because you've got that commonality of place across all these various environmental data sets.
Very well put. Anybody else wants to add to this question?
So perhaps just to say, one person's data is another person's metadata and the other way around. So and I think it's important to kind of acknowledge that there are certain things which just make sense to be put into a knowledge graph, and certain things which just don't make sense to be put in a graph structure, right? The obvious example I usually give is images, right? I mean, you don't want to encode the pixels as triples. That just doesn't make sense. Likewise, if you have raw data files, large collections of sensor data, then it needs thinking, kind of which parts do you want to put in the knowledge graph to make it fair, right? And which parts you should just kind of link to, as the original CSV sheet, for example, and things like this. So this is just one thing which needs thinking about. Generally, as a metadata data, the difference is really unclear because it's very fluent. But generally, the more things go into metadata, the more they're suitable for knowledge graphs, generally speaking. And then if we think about what you just asked, Krzysztof, namely to build something that is a large kind of US knowledge graph, right, which kind of could be one of the outcomes of this whole track in the end, or follow up funded work, then of course it makes sense to start with data that is of common interest, of larger interest. But then it's also important to make sure not only kind of what is in there, but that the way how it is in the graph also kind of really lowers the barrier for all the fair aspects, right? Which means you need to be kind of very conscious about what you're doing.
Actually, that leads me to a follow-up question that I hope you guys will find interesting. Pascal, you said data, metadata, then we are talking about knowledge graphs. You mentioned that this comes from the linked data cloud before and so on. We are talking obviously about integration of information and stuff like this. That's quite many terms, right? So what is the difference between data and knowledge in this context? Why don't we say data graph, right? But knowledge graph. We also say data science and not knowledge science, right? So what is the knowledge in knowledge graphs? What do you guys think?
Well, I'll jump in there because when we developed a very nice metadata specification in XML, we thought we had really solved the data integration issue. But that was not the case because people were talking about the same thing in different ways. They were talking about different things using the same terms. And so even though there was a lot of value in having a formal metadata specification, you can just think about the way somebody's name, for instance, might be referenced. And how do you know exactly who we're talking about until the ORCID identifier scheme really helping a lot with that. So for me, that translation from data to information kind of goes to the data having metadata that describes what the data are about, but the knowledge is further linking to very well-defined notions and relating to other aspects which provide even further additional context and clarification about what you're talking about in sort of a more of an aggregate and higher level of understanding than just the basic, for instance, scientific observation. I measured some sea surface temperature on such and such a date at such and such a place. You put it into that broader context, and that's where the semantics comes in.
I don't want to corner the discussion, but so perhaps to add to that, just so I mean, I think the knowledge in knowledge graph is as much a euphemism as intelligence is a euphemism in artificial intelligence. But that's just aside, right? But what is meant with that is that, well, kind of in artificial intelligence, it's kind of towards intelligence, right? In knowledge graph, it's towards knowledge. But that aside, one way of looking at this, and this is completely in sync with what Mark said, it's just a kind of different angle, is you want to try to make data as self-explanatory as we currently know you can do it. I think this is really key, right? Well, in addition to being automatically processable, and all the FAIR principles, but self-explanatory. And the way to do that is, as Mark said, through metadata, through expressive metadata and other mechanisms. But this self-explanatory is really the key point towards, well, making it more findable, right? Making it more interoperable, etc. Because you're not just kind of getting CSV files thrown at you and you see wind direction south and you wonder if it's to or from, just to give a simple example.
Well, fantastic answers. And I think that maybe this is not as widely clear, and that's obviously something that we could all work on, that this is what's meant by knowledge, right? It's this data plus metadata, and not just some metadata where you need the next metadata to understand what the metadata is essentially, but metadata enriched or described in some way that is both machine readable and reasonable.
And I would go a step further than that, Krzysztof. And I don't know if everybody agrees on that when I say this, but I think a really, really important aspect here is as well that the data organization is done in such a way that it resonates with the experts on the topic. I believe that is a key aspect of allowing reusability. And making it kind of proof for future and for updates and for reuse in different contexts and merging it with new data and so on. So it's not only the metadata, it's also it really is the computational artifact which we get, or the data artifacts which we produce, graph plus schema, is really between the data and the human conceptual level, to the extent to which we manage to do this at the moment.
Well, it could be even more radical, and the way I say it is that one of the key advantages of semantics and knowledge graph is that they get entirely rid of the data metadata distinction, right, which is a plague for many years. And Shirley, Thomas, I want to make sure that we also hear from you. Do you have ideas to share or thoughts to share on this question? Otherwise, I can just continue to the vocabulary side, which I guess Shirley is already waiting for.
We can move on to vocabularies.
Okay, we can go to vocabulary. Okay, so obviously we are in this nice flow, right? We started with FAIR, and then we talked about what goes in and what goes out, and then what the heck is data versus knowledge and stuff like this. And then Pascal and Mark talked so nicely about the need for self-description of the data using some sort of formal semantics. So what is the role of this formal semantics? What is the role of these ontologies or data or knowledge graph schema in really creating a widely usable knowledge graph across data sets? Shirley, maybe you go first if you like.
Okay, Mark and Pascal already really explained it very well. They said with respect to our previous question, ontologies are what make data graphs become knowledge graphs, right? Pascal said ontology plus data is a knowledge graph. And we have these classic definitions of ontologies that say they are formal frameworks for representing knowledge in a domain. They are used for interoperability. They can enable automated reasoning. But really, from a knowledge graph's perspective, I believe ontologies add that extra layer of knowledge, and this knowledge helps connect the dots in data. And I'm not sure a data graph as such as a standalone product can be best used for decision making without this knowledge. And because like again, reiterating, they are the ones that actually provide the semantics to the data. And Pascal mentioned this, saying it also adds context to the data. So having this ontology helps us understand what is the use case for this knowledge graph, or what is the data that it is being used for, and who is it for, like how is the data being used. And then you can add additional relationships, saying how can this data be reused with other data. And using an example from our KnowWhereGraph, like based on experience, we have all these like hazards and environmental data sets in KnowWhereGraph, and in their raw form, they come from all these different sources, and they have their own data models, but they're all very different. And in KnowWhereGraph, we use ontologies to stitch all this information together to provide a very cohesive view. And for example, we have Hurricane Katrina, which has impacts from one specific data set and trajectories from another data set. And the FEMA data set, which tells you about the financial assistance or other kinds of relief information that was provided for that specific event. But by modeling hurricane as a class in an ontology, we give additional context and knowledge about this specific event in our graph. And now we can ask questions saying, what were the impacts of Katrina when it made landfall in a specific spatial area? Now, of course, hurricane can mean different things in different ontologies. And one way of us adopting giving better sense to it is adopting standard specifications to model semantics. And again, this is what makes ontology, makes our KnowWhereGraph fair in a sense also, I would say. Yeah, so that's my perspective on the importance of ontologies. They help connect the dots in data.
Super. Anybody wants to jump in?
Yeah, I like thinking about ontologies as a way for scalable data management. And one example that I'll give is, I believe it's DBpedia, where it's really easy to add new facts to the database, but it's really difficult to add new predicates. And so in this sense, it provides a sort of guardrails for end users to input information. And this is also true with Golden, the distributed kind of Wikipedia competitor, where they have predefined guardrails for thousands of users to input information. And so I think it's a really great tool for scalable data management, where you have non-expert users entering information, and you essentially use it as a way to tell them what's possible and how to model reality. And it's up to them to fill in the appropriate information.
Just to add to that, Thomas, because that is such an important point, which I sometimes tend to forget. So essentially, you were mentioning that ontologies also serve as essentially constraints on the data, right? And this is extremely important. And again, this speaks to the kind of dual purpose they have, that on the one hand, they explain and they make the bridge to the human conceptualization. On the other hand, they constrain the data and inform as a schema the underlying graph, right? And it's the fact that they can be in this multi-purpose space, right, which I think makes it so powerful. So this is cool.
Okay, So one thing that I hear people often saying in this context, if you look at knowledge graph as web scale systems, and they're going to connect across many different data layers, from science to journalists, from world knowledge, so to speak, to the frontiers of science and so on. There will be also facts that maybe we, or I should maybe say statements and not facts, that we disagree on, right? And that may be true for the individual statements, but maybe also true for what we called these ontologies, right? So we don't all share the same conceptualizations of what is around us. How would you deal with this in such a web scale knowledge graph for the US?
I think that's one of the big advantages, Jano, is that it is a fact of life that people will have different notions about, what we think are common concepts. Two, for instance, that come to mind for me is, for instance, something like carbon dioxide flux. So many of us would be familiar with carbon dioxide flux in the context of global climate change. And but there, when you talk to researchers, they have different ways of measuring carbon dioxide flux, which are actually not compatible, right? They would require a conversion. But you could even broaden this notion of carbon dioxide flux, which also from more of a chemical and physiological perspective, you're talking about, for instance, carbon dioxide flux in the human lung, and which it determines how much CO2 is in your blood. So luckily, our semantic approach can enable you to look for carbon dioxide flux and then see all of the various potential definitions or perspectives on what might be meant by carbon dioxide flux, and basically then interpret and find relevant additional materials, whether you're a chemist who's interested in carbon dioxide flux, a physiologist, or a climate scientist. Another favorite example of mine is forest, which is really necessary to understand, actually climate change and the rapid disappearance of forests around the world, and how the definitions of forest can change a lot depending on whether you're the United Nations FAO or the USGS, or some small county level group in the United States that's trying to preserve some of its wildlands. But all of those can be accommodated thanks to the various structures afforded to us by RDF, and as well as using some of the formalities of things like SCOS, which gives you the opportunity to say this is related to, or this is narrower than, if not going, a formal, class, subclass, or alternate label kind of all very, very standard ways to represent those relationships in these W3C languages.
It is one of the most fascinating things for me when doing ontology modeling with interdisciplinary groups, to kind of get at the types of differences, Mark, which you've just mentioned, which just go beyond easy factual stuff, which of course can also be like if two historians disagree on the birth year of Shaka Zulu, right? That's easy to handle in a knowledge graph, right? But the conceptual stuff, which Mark mentioned, and kind of we tend to say that you should have, when you do ontology modeling, you should have at least 2 domain experts in the group who do not always agree, right? And then one of the most fascinating things is making a model they can actually both agree on. And yes, it's possible, though it's not always easy. Like for example, and then of course you get these notions where, but as Mark said, they may have different underlying definitions. There may be notions which are everyday notions, but they actually can't really define what exactly it is, right? Like, for example, working with ocean scientists, they were always talking about water columns. They weren't really, it's not a clear notion, right? It's really hard to model that, right, in a classical sense. But it's a central notion, right? For example, so and this is very fascinating. But yes, needs some effort on the modeling side.
Well, super. And that brings us to a very interesting follow-up question, namely how to scale this, right? obviously, if we would have what you just described, Pascal, that we have the two right people in the room and they have their conflicts and their agreements and you see them converge, that would be wonderful. But maybe 2 is not the right number to represent a larger domain, maybe 5, maybe 10. So we have done these vocabulary camps all here together in the future. But the question is still, how would you scale this? And what is the role of novel techniques like, for instance, from machine learning or presentation learning that we could maybe add to what we are doing top down to scale the creation not only of assertional knowledge but also of the schema knowledge?
So since you mentioned me, I have a complex answer to this. Bear with me. There was an old school idea around that, and the old school idea is from the kind of beginning time of the semantic web world. And the old school idea was, well, we just need to make ontologies everybody agrees on. There's a pre-semantic web school of thought, which essentially we know now doesn't work, which was we just make one knowledge base for everybody. We now know that doesn't work, right? But then about 20 years ago, it was all by we need to make ontologies everybody can agree on and then use, right? And then you make this effort once and then it's done. And in my opinion, it was good that we tried it out, right? But this hasn't really worked. It has worked for some areas, for some specific corners, but in most cases it doesn't. And most ontologies which are out there modeled with this mindset essentially were one-shot ontologies. So they were made for one specific purpose, which makes you wonder why you just didn't kind of use a database. But okay, we're wiser now. So these days, kind of the mindset, I believe, needs to change and is changing. So one of them is you don't try to model it for everybody. You acknowledge that different use cases have different requirements on the graph schema, right, and in the graph shape. And while you're still trying to organize your data and your knowledge graph in a way that it can be rather flexible and cover more than one use case and several use cases, it's important to just consciously acknowledge that there is a certain limit to what you can do in that way, which essentially means you need to have some other ideas how to do the scaling. And the ideas kind of which I would put forward, which kind of in my mindset to this are, on the one hand, make a schema that is easy to adopt, but one where yeah, you will have to adopt it, but it's easier to adopt. Make a graph that's easier to adopt than previously. And then more importantly, also, don't think of ontologies as things that, an ontology that everybody can do, but think of little central pieces of an ontology that can be much more widely scaled. We call these modules. And we make these modules often out of design patterns, which can be much more widely used. They're very small snippets, like how do you encode, say, the relationship between persons and their organizational affiliations? That would be a little pattern. Or how do you encode a sequence? So there's probably 3 or 4 ways, of doing that, which kind of makes sense. Call this a pattern, which you can easily reuse. So if I make an ontology, I need to encode a sequence. I have these patterns I can look up and say, well, this one works for us, right? And then it will often also work for others because they are carefully designed patterns and modules which kind of work over a wider context. And you can just take those pieces without having to subscribe to the whole ontology, 80% of which may not really be that central and important for you.
Yeah, absolutely agree. And I think that is spot on. Anybody wants to add something here?
Yeah, I'd like to expand into the middle ground. I think that Pascal just said, the global one to rule them all didn't really work, and we got to go modular because, and I think that there's a middle ground, and perhaps best represented by the gene ontology and KEBI, with just the chemical ontology, which both of those I think are quite useful to a relatively focal domain. But were it not for those, I think there would be a lot more confusion, certainly relative to the gene ontology, which nicely forces you when you're proclaiming you found a gene to talk about where it is and what it does using a standard set of terms. And if what it does is not there, you have to formally apply for, a new term to properly represent this new type of relationship you've found. So I agree that the one ontology to rule them all is, problematic. And the modularization, maybe modularization up at the level of some, discipline that has a need and has the expertise to do it properly, as exemplified by the gene ontology primarily, and also the Kebi ontology.
To some degree, you could call us version 3 of the entire endeavor, right? First, the classic semantic web, then the linked data stuff, and now the knowledge graph incarnation. And of course, this is how science and industry and knowledge progresses in general. But it's important also to look back. So reflecting back on version 2, or maybe even version 1 of linked data and semantic web, what have we learned that this time we believe that's going to be a success now?
Well, I think in the area of environmental data and all of these environmental data repositories, as we mentioned earlier, that FAIR paper really galvanized people. For some reason, I mean, I think it's something all of us knew was important, but it just kind of put an acronym and defined different facets of the challenge. And so I think that the awareness of the value of trying to make your data fair, and then how do you do it? There were lots of hints in that paper about how to do it. And we're the ones, I think, that are very much pursuing exactly down those lines. So I think it was just the broader awareness and proclamation. You see this at the research data, the International Research Data Alliance, for instance. They're very concerned about FAIR, and they've got several working groups that are focused on semantics. So it's the same thing at ESIP, where there's been, a burgeoning of groups focused on semantic approaches. And so I think that just finally it's dawning on people. They're getting understanding about how graph technologies work, about the importance of the W3C recommendations. Took a long time, but I think it's finally happening.
Yeah, there's a couple of, I mean, it's a very multifaceted question, right? I mean, we've learned a lot. We've also learned a lot what not to do over the last 20 years. So that's important. Kind of mentioned some of those earlier already. But I think there is another substantial difference between the knowledge graph trend going on right now and the linked data trend, which we had 10 years ago and or 12. And the ontologies trend, right, which was 20 years ago. And I think one difference is that while there was always a lot of industry interest, right, there has always been a lot of industry interest, this time what industry is doing is production level. And that really makes a difference. And that probably means that the Gartner projections from 20 years ago about semantic web technology will be mature in 20 years, we're probably not that far off.
Anybody else?
Pascal, what you probably know the history, but I think when Google kind of said, "Oh, we have a knowledge graph," when they kind of purchased Freebase, which was an unfortunate name for a database, but that kind of also was like, oh, Google has a knowledge graph. I sort of introduced that term into the popular purview, I think, didn't it?
Yeah. So, and I mean, they were the leader, and then a few years later, there was this paper which I always like to cite in ACM, in communications of the ACM, which were several IT multi-globals, right, including Google and eBay and Amazon and Microsoft, who talked each in the same paper about their industry internal knowledge graph and their importance about it, right? So this is one thing, and of course, they wouldn't expect that invest that lot of money if there weren't the outflow at the end, right, in terms of added value. But also, for example, the fact that Amazon Web Services now with the Neptune triple store, right? I mean, there have been triple stores around for whatever, how many years you want to think, but they were always by small companies, by spin-offs and so on, and that was fantastic, of course, right? But now seeing a major player who really kind of gets on the field and is doing a lot there, that's also a changer, right? That changes significantly. And then you have other companies like TigerGraph, for example, which is also pretty substantial size already as a startup. So this really changes things. I think there's still a lot that could be done in terms of tool improvement, but I'm very optimistic now that this will come.
Well, you're making a very interesting parallel also to, for instance, what's going on currently in this metaverse thing, right? Where suddenly, Facebook rebranded to Meta and are picking up something as a new idea, which has been around for, 20 years and also with various startups. And now suddenly it's gaining steam. So sometimes a very big flagship, of course, helps clear the storm, so to speak. So I agree, that's a good observation. So we were obviously very optimistic in most parts of the session, and we only have 3 minutes left. So let me ask a more gloomy question, so to speak. What are the biggest challenges on the horizon? I hope to hear, because this is our last question from each of you. What are the biggest challenges on the horizon for developing this proto open knowledge network as a web scale decentralized network for the United States?
I'll go real quick. I think that for me, it's twofold. It's the scalability, which is going to lead to challenges in query resolution, and it's building effective user interfaces to enable the common person out there, and not just the experts, to effectively access the graph.
I think that consensus will be a really big problem. It's already a problem in so many places, and the knowledge graph community, I think is fragmented on different levels. On one hand, there are so many different products out there. We could all name a dozen recent startups. We could name half a dozen different query languages, and even the technology itself is fragmented between LPGs and triple stores. And how does all of this come together? And I think we're at least seeing improvements. We're seeing kind of abstraction layers emerge on top, like Gremlin. And so, yeah, I think as time goes on, kind of the victors will emerge, and we'll probably, have more of these abstract layers on top, which should hopefully really help.
I think based on our experience with KnowWhereGraph, one of the biggest challenges that I see is maintenance, because knowledge graph construction is not a one-time effort. It's a life cycle that you have to constantly, that you need to constantly make sure that the data is updated, that the data is clean. Sometimes semantics may change. And so the concern that I see with constructing a big knowledge graph is the cost associated with maintenance, and also the fact that there are no really good tools out there that can be used for, constant update, continuous update. That's data translation.
Good point.
All very, very good points, I think. So any closing remarks? Obviously, we only made it through half of the questions that I prepared, and I think we could have, easily made this a 90-minute session. And to a certain degree, I think, once we can all meet in person again, having this in an in-person setting, as maybe even a recorded event like the one here, talking a little bit about the philosophy of knowledge graphs would be really, really great. So, any famous last words before we stop the recording? I was betting on you, Pascal, but then thank you so much, everybody, for listening, and for all of you in the future who are going to also look at these recordings. Thank you so much for NSF and others for organizing these expos, and bye-bye, everybody.
Thanks.
Thank you.